Good evening. My name is Christian Gomez Macias, and my student number is 2173-48087. This is the dynamics assignment number 1. The initial concept of this elevator setup is shown in Figure 1. The elevator E and the objects collectively have a total mass of 400 kilograms. The hoisting mechanism is facilitated by the motor M and the 60 kilogram block C, with a motor efficiency of 0.6. So the questions are: determine the power that must be supplied to the motor when the elevator is being hoisted upwards at a constant speed of VE is equal to 4 meters per second, and what are the shortcomings in this plan? Please explain. So as with any problem, we always want to start with our givens. The mass of the elevators plus the objects have a combined mass of 400 kilograms. The block C has a mass of 60 kilograms. The motor efficiency is 0.6. The gravity is 9.81 meters per second squared. And the constant speed is VE is equal to 4 meters per second. And due to having constant velocity, we can assume that the acceleration will be 0. Next up, we have the free body diagram. I began with block C here. We have the weight of block C, which is acting downwards, and the tension of block C. And then I drew the elevator shaft itself. We have the weight of the elevator here, acting downwards in the middle. And then we have an interesting array of tension forces acting in the upward direction. We have tension 1, tension 2, and tension 3. And the reason why there's 3 tensions acting on this is due to the way we solved the elevator problem in the tutorial. In the tutorial, we had 1 tension here, 1 tension here, and 1 tension here. But due to the way that they're all connected by one single rope, these tensions are actually just a summation of each other. So we could just say that these are 3T. And the TC that we see as the 4th tension is just the tension acting as block C. Here is TC. So WE is the weight of the elevator times the gravity. WC is the weight of the block C times the gravity. T1, T2, and T3 is the tension of the elevator, or the total tension. TC is the tension of block C, and later I realized that because of the way that the problem is set up, TC will be equal to WC, so we don't have a use for WC here. We will just be using TC to solve these problems. So next up, we have the useful formulas for solving this problem. We have Newton's second law, which is the summation of the forces acting in the y direction is equal to mass times acceleration in the y direction. The tension is equal to T is equal to mg, which is mass times gravity. Weight, W, is equal to mass times gravity. And the power required formula, we have P is equal to T, where T is tension, times V, where V is the velocity of the motor, and E is the given efficiency. So now solving the problem. So first things first, we have the weight of the elevator. We can convert that to newtons by multiplying the 400 kilograms times 9.81 meters per second squared, which is 3,924 newtons. Next up, we have the tension at block C, which is equal to mass times gravity. It is given, it's 60 kilograms times 9.81 meters per second squared, which gives us 588.6 newtons. So also worth mentioning, this is supposed to be a negative force because it's acting downwards, while this one here is a positive force. The summation of the forces acting in the y direction is equal to the mass times acceleration in the y direction, but earlier we had discussed that the acceleration in this problem is 0 due to the speed or velocity being constant. So we have the summation of the forces acting in the y direction is equal to 0. So now we can just add up the forces in the y direction and do a little formula manipulation because of the way that the tension is distributed. So we have TC, which is an independent tension. T1, T2, and T3 can then be grouped together to form the 3T that we have over here. And we have the weight of the elevator acting in the negative or the downwards direction. And this all equals 0. So the tension at block C plus the three tensions connected to the elevator minus the weight of the elevator is equal to 0. We can now plug in the values we found earlier, which is 588.6 newtons plus 3t minus 3,924 newtons equals 0. Now the what we're looking for here is to solve for the total tension T. So we have to isolate for it. So if we move 588.6 newtons to the right side and 3,924 newtons to the right side, we then end up with 3,335.4 as the difference. And we still have this 3t here, so we can isolate for t by dividing both sides by 3. Now t is equal to 3,335.4 divided by 3, and the final value for the tension will be 1,111.8 newtons. This is the tension in the cable connected to the motor, and now we can solve for the velocity of the cable attached to the motor. So I've drawn another free body diagram to sort of explain my thought process here. We have, because of the pulley, we have one velocity of the elevator acting upwards, 2 and 3 acting upwards, and we have the velocity of the motor acting downwards because it's at the top. So we have the 1 negative velocity and the 3 positive velocities. So we can combine these 3 to become their own entity. So we have the velocity of the motor is equal to 3 times the velocity of the elevator, and the velocity of the elevator was given at the beginning of the question. It is 4. So we can just multiply 3 times 4 meters per second to obtain the velocity of the motor, which is 12 meters per second. Now we can find the power required that must be applied to the motor using the formula P is equal to tension times velocity of the motor divided by the efficiency. So P is going to be equal to 1,111.8 newtons times 12 meters per second divided by the efficiency, which is 0.6. And the total, or the final value that we get, is 22,236 watts. Because this can be converted, I'm going to be converting it to kilowatts. The conversion factor is 1 kilowatt divided by 1,000 watts. So we have 22,236 divided by 1,000. We get 22.236 kilowatts. So therefore, the power that must be supplied to the motor when the elevator is being hoisted upwards is 22.236 kilowatts. Now for part B of the question, the shortcomings in this plan. Number one, there may not be sufficient power to properly power the motor due to the potential of mechanical losses in the system. Specifically, the friction found in the pulleys and gearboxes may reduce the overall efficiency of the motor. These issues, if not maintained, could lead to reliability issues with the motor and potential failures. So what I mean by this is that the pulleys in the elevator, if not maintained properly, they might suffer from, say, rusting, which might affect the way that the cable moves, and the efficiency will go down. And due to this problem being so perfect and so focused on the perfect model, if there's just a little bit of rust or maybe some weather damage, some corrosion, then the pulley here will create some resistance or some friction, which will make the cable need a little bit more power to properly do its job. And the final power that we receive from the plan will not be the final power needed, it might be more. Also, the fact that corrosion or rust might damage the cables, and it might lead to a potential failure in that sense as well. So number two, the load of the elevator will vary depending on its contents and the people riding it. This effect will be specially noticed if the center of mass is not properly centered, causing the motor to struggle or jerk the elevator. So what I mean by this is that, let's say that this is the elevator here. If someone gets on and they decide to stand off to the side, because I stand off to the side when I'm in an elevator, I don't just stand directly in the middle. So if someone stands off to the side, and let's say that they have a heavy backpack or a mobility scooter, and they're standing off to the side, well, there's now a tilt in the right side, which is not accounted for by the plan, because the plan expects all the weight to be evenly distributed down the middle. But in the off hours, when there's not that much traffic, people will stand off to the side, and there will not be someone to counterbalance on the left side. So in this case, the because of the elevator is not properly centered, the motor is going to have to work in overtime, and it will need either more power or less weight. Um, it won't be able to function properly. It might even jerk the elevator up and down, or it might not move it at all. So, because the plan is so perfect and in need of um, center of mass being in the middle, this plan won't work if someone decides to stand off to the side or if it is generally unbalanced. Thank you for listening to me. This has been Christian Gomez Macias, 217-348-087. Have a good night.